Hello, dear students. Today, let us learn the configuration of a continuum, the material, volume or material arc or material surface, velocity, and the concept of motion of a continuum, the velocity and acceleration, and material time derivative and local time derivative, and the relationship between them. Okay, let us understand what is called the continuum concept. Okay, configuration of a continuum. Let us consider a continuum, okay, occupying a geometrical region. Fine. Continuum could be any physical object at a given instant of time. Then every part of the region is filled by some part of the continuum and vice versa. That means what? There is no gap at all, right? So every gap or every point in that region is occupied by a part of the continuum. There is no vacuum in that physical object. That is first assumption. Okay. An infinitesimally small part of the continuum is called material point or a particle. Thus, continuum can be regarded as connected set of particles. Connected, very important, right? So there is no gaps. So everywhere there is particle, and every particle of the continuum can be regarded as a position in the region R occupied by the continuum. Every particle of the continuum can be regarded as a position, and every point in the position is made up of some particle of the continuum. So there is a 1:1 correspondence between the particles of the continuum and the points of the region occupied by the continuum at a given instant of time. Let us see what is a material curve. A part of the continuum whose position is a geometrical curve is called a material curve. So in the continuum, if you take any curve, right? So all the points on the curve will be some point, some part of the continuum. Particles, it will contain particles. So any part of the continuum whose position is a geometrical curve is called a material curve or material arc. A part of the continuum whose position is a geometrical surface is material surface. A part of the continuum whose position is a region or volume is a material body or material volume. Material element is nothing but a small, very small, infinitesimally small volume element of a material body referred to as body element or material element or material volume element. Okay. Now let us see what is mass and density, how they are related. These two physical quantities are positive scalar quantities. Density is denoted by rho and is defined as rho is equal to limit delta m by delta v as delta v goes to 0, where delta m is the mass of the material element, delta v is the volume of the material element. So clearly, this density is a function of both position and time. If V is constant, if the volume is constant, then the total mass of that continuum is given by this volume integral rho dV. Volume integral rho dV. Now let us see what is a motion of a continuum. Let us take a continuum. Let this continuum C fill a region R0, fill a region R0. Let me draw it. So this is R0, okay, at time t equal to 0. The same continuum after some time could have moved. Okay, we are considering motion. We are considering motion. So the same continuum fills the region R at a time t. Suppose this material point, which was at the position x naught, this is the position, okay, at x naught. Now this is a continuum. Let us take a material point, some material point. Say this is a material point. We are calling it as M. If this point M, which was at the position vector x naught at time t equal to 0 in the region R naught is moved, it is moved to the position, x at time t in the region R. Okay. Now there is a displacement. Let us take what is u. U is the difference between the position vectors, right? Positions x minus x naught. U, x and x naught are vectors. So we can fix a suffix over there, right? So ui is equal to xi minus xi naught. I equal to 1, 2, 3. I equal to 1, 2, 3. This u is called what? Displacement of that material point M, where these xi naughts, this naught has to be super suffix here. This naught no, should be super suffix. So these xi naughts, x1 naught, x2 naught and x3 naughts, these are called the initial coordinates or material coordinates or reference coordinates, where xi's, x1, x2, x3 are called current coordinates or spatial coordinates. And these spatial coordinates are definitely at t greater than 0. The transformation, this transformation, or in other words, motion of a continuum from one region R0 to R is described by the equation, the following equations 2 and 3. Just look at the equations 2 and 3. So what is equation 2? Equation 2 has xi, right, in terms of xi naughts and t. And equation 3 is xi naughts in terms of x1, x2, x3 and t. So it is assumed that the transformation given by these two equations exist and they are continuous and they are unique. That's an assumption. Whenever there is a motion, we assume that the transformation exists, right? And they are continuous and they are unique. The transformation given by 2 and 3. Look at equations 2 and 3 again. So remember our 2 is xi in terms of xi naughts and t. And equation 3 is xi naughts in terms of xi's and t. Right? So these two equations, the transformation exists only when the Jacobian of the transformation is not 0. Is not 0. What is Jacobian? Jacobian is nothing but denoted by J. It is nothing but the determinant dou xi by dou xi naughts. It is not equal to 0. And in equation 2, xi naughts and t are the independent variables, and it specifies the particle xi that occupies the position xi at t greater than 0. And equation 3, xi and xt are the independent variables, and it specifies the particle xi naught, right, that occupies the position xi naught at time t equal to 0. So in equation 2, when equation 2 is used to study the motion of the continuum, then that approach is called Lagrangian approach. When equation 3 is used, then the approach is called Eulerian approach. In the Lagrangian approach, the attention is focused on the individual particle and observe the status of the particle as it moves. On the other hand, Eulerian approach, the attention is focused on position point in the space or region of interest and observe the status of the position as time progresses. As time progresses. In Lagrangian approach, we determine the history of every particle, right? In Eulerian approach, we observe the change in the state of fluid as it passes through that point. So in Lagrangian approach, particle is fixed. In Eulerian approach, position is fixed. Let us see what is local time derivative. Consider a real valued function. Let us take a real valued function phi, which is function of x's and t. What are x's? X's are spatial coordinates of a material point. Then the local time derivative of phi, denoted by dou phi by dou t equal to dou phi by dou t. What are fixed is very, very important. X's are fixed. X's are fixed. Then that is nothing but local time derivative. So local time derivative is nothing but rate of change of that function with respect to time when x's are fixed. Very, very important, x's are fixed. If phi is function of r and t is the fluid motion, keeping xi is fixed, that is r is fixed. Okay, then the change in phi is nothing but, just watch. So what is fixed? R is fixed, so R, and here also R, right? So we have phi is equal to rate, the change in phi is nothing but phi of R comma t plus delta t minus phi RT. Remember, R is fixed. Then its rate of change is nothing but limit delta t going to 0, phi R is fixed. See, R is fixed and here also R is fixed. So phi of R t plus delta t minus phi RT divided by delta t. And this is nothing but the differentiation, right? The partial differentiation with respect to t. So dou phi by dou t. Dou phi by dou t. And this is the local time derivative or local time rate of change at that point. Let us see what is material time derivative. Material time derivative, consider that same function, right, phi. Now here the phi is function of xi naughts and t. Xi naughts are the material coordinates of that material point. Then the material time derivative is denoted by d phi by dt, capital D phi by dt or small d phi by dt. You can use any notation of this. So d phi by dt is nothing but differentiation of phi, partial differentiation only, but what are fixed? Xi naughts are fixed. Material coordinates are fixed. So, and this d phi by dt will be function of xi naught and t. Suppose our phi is function of r and t. Suppose you take in terms of r and t is the fluid motion. Keeping xi naughts fixed. Okay, then the change in phi is nothing but c, r plus delta r, and there is r. You have to take both the changes, change in r and also change in t. Change in t. So phi at r plus delta r comma t plus delta t minus phi at r and t. Right, that is the change in phi. The rate of it, the change is nothing but limit delta t going to 0, same denominator, numerator divided by delta t. And this is d phi by dt, capital D phi by dt. And this is material time derivative. So we learned local time derivative and material time derivative. Okay, let us see what is velocity and acceleration. In the material description of motion, we have xi. In the material description of motion, we have xi in terms of xi naughts and t. Xi naughts are the material coordinates. Then vi, the components of velocity, is equal to dxi by dt, capital dx by dt. It is nothing but differentiation of xi, right, with respect to t. What are fixed? Material type rate, no. So it is xi naughts fixed. Material coordinates are fixed, where vi are the components of the velocity vector v. So equation 5, vi we can write as dxi by dt in terms of xi, the spatial coordinates. Also, we can write down this vi's in terms of the displacement. Let us see how. We have ui equal to xi minus xi naughts, displacement vector u, right? Ui is equal to xi minus xi naught, I equal to 1, 2, 3. So what is xi equal to from this equation? You are going to get, you can just put, take xi naught to that side. So it becomes xi equal to ui plus xi naught, right? So substituting for xi in equation 5, in the place of xi, we can put this ui plus xi naught, right? So substituting 6 in 5, what is happening here? So in the place of xi, you are putting this. So ui plus xi naught delta t, what is fixed? Xi naught fixed. Now we'll separate. Now we are going to take dou ui by dou t plus dou xi naught by dou t in the next step. Okay. So we have the first part plus the second part. Second part is 0. Why this is 0? Because xi naughts are fixed. Xi naughts are fixed. Therefore it is 0. This whole thing is 0. So what we are going to get? We are going to get dou ui by dou t. What are fixed? Material coordinates are fixed. So whenever the material coordinate phase is fixed, material coordinates are fixed, this is nothing but the material, the rate of change. So capital D by dt of ui. So what is our LHS? LHS is ui. Vi is also, in terms of displacement, it is also the material time rate of ui. Capital du I by dt. That is in terms of displacement. So V1 is du1 by dt, V2 is du2 by dt, and V3 is du3 by dt. And these are the velocity components. Or you can also say material velocity. So we can have in terms of displacement or in terms of the spatial coordinates, x's. Let us see what is acceleration. So rate of change of velocity is nothing but acceleration. So A is dv by dt. So A1 is V1, A2 is V2, and A3 is V3. So these are the acceleration components. So this is material acceleration. Now let us see what is the relation between material time derivative and local time derivative, or material time derivative in terms of local or spatial time derivative. And very, very important relation and very easy also to prove. Let us consider a fluid motion, okay, associated with a scalar point function phi, which is function of r and t, where r is the position vector x comma y comma z, and our phi is function of x, y, z and t. So what is the total differential d phi? D phi is dou phi by dou x dx, dou phi by dou y dy, dou phi by dou z dz, dou phi by dou t dt. We'll divide by dt. So divide by dt. So everywhere dt has come. Dt has come. And here dt will get cancelled. So there is no dt here. dt got cancelled. So what is d phi by dt? D phi by dt is nothing but capital D phi by dt. That is material time rate of phi. So dou phi by dou t is written first. the remaining as it is. We'll call this as equation 7. Okay, now we'll find what is this, equation 7, this part. We'll find what is this, and we'll substitute here in equation 7 for this part. Okay, so for this, let us consider the velocity of the fluid. Let us call it as q, and we know that q is dr by dt. Q is nothing but dr by dt. Okay, and r is nothing but xi, yj plus zk. So what is dr by dt? Dr by dt is nothing but dx by dti, dy by dti, and dz by dtk. And q is nothing but ui, vj, wk. Fine. So just equate the corresponding coefficients of I, j, k. This has to be I here, j here. This is j. Okay. So now u is nothing but dx by dt, I components. Now equate the j components. J components is v equal to dy by dt, and w is equal to dz by dt. Okay. Now take the dot product. What is the dot product? The dot product is del phi dot q. So we'll take del phi here dot q dot q. Fine. So take the dot product now. Take the dot product. Our q is in terms of u, v, w, and u is dx by dt, v is dy by dt, and w is dz by dt. That's taken in terms of q there. Okay. That is how that q has come there. So take the dot product. So dot product will have only what? That's nothing but dou phi by dou x into dx by dt plus dou phi by dou y into dy by dt, dot product, right? Ordinary dot product plus dou phi by the k components, right? So dou phi by dou z into dz by dt. Fine. So look at equation 7. So we had marked this in blue line, blue. So in the place of that, now I can just put this part. I can just replace in equation 7 that whole thing, whatever we have marked in blue, as the del phi dot q. Fine. So using that, using equation 8, 7 becomes what? 7 becomes, so in that place we have put this. So what is LHS? This LHS is nothing but the material time derivative. RHS, the first part, is the local time derivative plus q dot del phi. This is the relationship between material time derivative and the local time derivative. Or in other words, material time derivative in terms of local time derivative. Okay. Now let us see what is the relationship between spatial and material acceleration. Now, in the previous relation, now this is our material time derivative and the local time derivative, the relationship between these two. Right, fine. Now in the place of y, we'll put vi, the components of velocity in this equation. Just substitute in the place of phi, we'll put vi. Why we are putting vi? Because I want acceleration. And vi is nothing but q, the velocity, another notation. So dq by dt is equal to dou q by dou t plus q dot del q. Equation 10. Fine. Now, in this equation, this is our equation 10. Now, what is equation 10? So, I have, LHS. This LHS is nothing but, material acceleration. And in the RHS, the first part is the local acceleration or spatial acceleration. Now, this identity, right, this second, part, q dot del q, we'll find what it is and we'll substitute here. Okay, now for this, we'll take the identity. We have the vector identity. Remember this equation 10. So in the equation 10, I'm going to take this and substitute something else. Let us see what is that. So consider the vector identity. We have, gradient of A dot B is this, equation 11, for any two non-zero vectors A and B. Now this identity happens for all vectors. Now just replace B by A in the same, identity. So everywhere it is A now. So there's no B, everywhere it is A. So these two are same. These two terms are same, so it is twice here. Okay, and again minus minus, again these two terms, this and this are same, so again twice there. Fine. So divide by 2, dividing by 2, you're going to get what? So half gradient of A square is equal to, now just that 2 is gone. Fine. So what is this now? We'll shift this to that side. Shift this to that side. So we get what? A dot gradient A. So we get A dot gradient A is equal to gradient of that half is taken inside. So A square by 2 plus curl A cross A. Fine. This is our equation 12. Now this is happening for any vector A. Now replace that vector A by Q. Q is also a vector, no? We'll replace A by Q. So we get Q dot del Q is gradient Q square by 2 plus curl Q cross Q. Fine. So remember in equation 10, now we will replace that part in equation 10. So equation 10 becomes LHS, material acceleration, equal to, this is local acceleration, plus what we got from the identity, that is gradient of Q square by 2 plus curl Q cross Q. What is curl Q? Curl Q is nothing but the vorticity, right? We denote it by omega, right? So just replace now. So we have the acceleration. What acceleration? Material acceleration is equal to local acceleration plus gradient Q square by 2 plus vorticity cross Q. This is the relationship between material and spatial acceleration. Now let us study different cases. If omega equal to 0, that means what? Curl Q equal to 0. Whenever curl Q equal to 0, just now we know by the basics, Q is irrotational. If Q is irrotational, then what happens? This part is gone. This whole part is gone from equation 13, right? So what is remaining? We have local material acceleration is equal to local acceleration plus gradient of Q square by 2. This is only the relationship between these two if Q is irrotational. Okay. Second case, if the motion of the fluid is steady, that is time independent, and irrotational, that is omega equal to 0. If the motion of the fluid is steady, that means what? This part is 0. This part is 0. That is dou Q by dou T is 0. So that is also 0. Omega is also 0. So we get material acceleration is equal to this much, gradient of Q square by 2. So if the motion of the fluid is steady, then the local acceleration is 0. Now third case, if the motion is steady, irrotational and uniform. Uniform means what? Gradient Q equal to 0. So gradient Q square by 2 is also 0. So we get material acceleration is 0. These are different consequences or different cases of the motions. And what is happening to the acceleration and the relationship between acceleration, material acceleration and spatial acceleration. Let us see what is called potential flow. If the velocity q can be expressed as gradient of a scalar function, that is velocity is gradient of some phi, then that motion is said to be potential kind or potential flow, and that phi is nothing but velocity potential function. Okay, so whenever the q is gradient phi, what is curl of q? Curl of q will be curl of gradient, and we know that the curl grad is 0, no? So therefore the irrotational motion is of potential kind, or is an example of flow of potential kind. Flow of potential kind. Okay, so in the next class we are going to take up problems on these. Okay, today we shall stop.